One of the most common uses of matrices is for solving systems of equations. A small system like 2 equations and 2 unknowns you can do by hand, but when you have more equations than that, like 5 equations and 5 unknowns, you'll need to use a computer and a method that involves matrices. Here we have 2 equations involving the unknowns x and y. Let's go through a systematic way of solving these equations, just looking at the equations, not using matrices, and then we're going to generalize on this technique and put it into a matrix format. The first thing I'm going to do is to take my second equation that I started with and subtract 2 times the first equation. So that's going to give me a new second equation. I'll be taking 2x and subtracting 2 times the x term in the first equation. 2x minus 2x will give me 0, which is why I don't have an x term in my new second equation. With the y terms, when I do equation 2 minus 2 times equation 1, I'll have 5y minus 2 times 3y. That's 5y plus 6y, which is 11y. And with the numbers on the right, when I do equation 2 minus 2 times equation 1, I'll be getting minus 3 minus 2 times 4, which is minus 3 minus 8, or minus 11. So doing this step has produced a new second equation. The next step I'm going to do, and I'm not explaining now why I'm doing these steps, just follow the arithmetic. The next step I'm going to do is just to multiply equation 2 times 1 over 11. 11y becomes y, minus 11 when multiplied by 1/11 becomes minus 1. And then the final step I'm going to do is to do equation 1 plus 3 times equation 2. Here's my equation 1, here's my equation 2 at this point. When I do this step, I'll be doing x plus 3 times 0 is x. I'll be doing minus 3y plus 3 times equation 2 means minus 3y plus 3y is 0. And when I work with the numbers on the right, I'll be doing equation 1 plus 3 times equation 2 will be 4 plus 3 times minus 1. 4 minus 3 is 1. So after performing these 3 steps, I have converted the 2 equations that I started with into the 2 equations x equals 1, y equals minus 1. And the value of that is obvious because when I've got them into this form, I can see what the x and y values have to be. X has to be 1, y has to be minus 1. Here I'm showing what's called the augmented matrix for the system of equations. The augmented matrix includes all the numbers, the coefficients, and the numbers on the right, and they're just arranged in a matrix in the obvious way. The first column is the x coefficients, the second column is the y coefficients, and the third column is the numbers that are on the right sides. So you can think of this little vertical line right here as sort of a separator that represents the equals marks. And we're going to go through those same operations on the equations, although now we'll be talking about operations on the rows of the augmented matrix. A moment ago, the first thing we did was to do the second equation minus 2 times the first equation. So now we're going to call that row 2 minus 2 times row 1. We're operating on the rows of the matrix. And when we say row 2 minus 2 times row 1, what we mean is we're producing a new row 2 by taking the old row 2 and subtracting 2 times row 1. So that will give us for our new second row 2 minus 2 times 1 is 2 minus 2, which is 0 in this spot. The 5 will become, when we do row 2 minus 2 row 1, 5 minus 2 times minus 3 is 5 plus 6, which is 11, which comes in this spot. And the minus 3 will become minus 3 minus 2 times 4, minus 3 minus 8 is minus 11 in this spot. So that first row operation corresponds to the first operation we did with the equations a moment ago. When working with the equations, we multiplied the second equation times 1 over 11, so now that translates into a row operation, multiply row 2 times 1 over 11, so this row 2 becomes this row 2. And then the final step we did a little bit ago was to get a new first equation by adding the first equation to 3 times the second equation, and that now becomes row 1 plus 3 row 2 as an operation on the rows of the matrices. Continuing from this point, row 1 plus 3 row 2 will give us a new row 1, which is old row 1 plus 3 times row 2. 1 plus 3 times 0 is 0. Minus 3 plus 3 times 1 is minus 3 plus 3, which is 0. And 4 plus 3 times minus 1 is 4 minus 3, which is 1. So we produced a new row 1 as old row 1 plus 3 times row 2. The notation R1 plus 3R2 means we're getting a new row 1 by adding the old row 1 to 3 times row 2. Keep in mind, when you write down the row operation, the first named row is the one that's being changed. In this step, we created a new row 2. Row 2 is mentioned first. In this step, we created a new row 1. Row 1 is mentioned first. There are 3 kinds of row operations that we'll use. One of them is just multiplying a number times a row. You've seen that one. For example, 7 times row 2 would be a valid row operation. That's equivalent to just multiplying an equation through by a certain number. The second type row operation that you saw was to combine 2 rows in a manner like this, row 3 minus 3 times row 1, for example. And the third row operation that we haven't yet had need to do is to swap 2 rows. This notation simply means swap row 2 with row 3. We'll see instances where that's necessary. This is a system of 3 matrices with 3 unknowns x, y, and z. So when we set up the augmented matrix for this system, we'll need a column for the x coefficients, a column for the y term coefficients, a column for the z term coefficients, and a column for the numbers on the right. The augmented matrix has 3 rows because we have 3 equations, and it has 4 columns. I want to outline the strategy that we're going to use. We start with the augmented matrix, and we'll first do a row operation to produce a 1 in the upper left-hand corner, the row 1, column 1 position. Then we'll do additional row operations to produce zeros at the other places in column 1. We move to column 2 and use a row operation to put a 1 in the row 2, column 2 position. And then we do row operations to put zeros at the other spots in column 2. We move to column 3 and use a row operation to produce a 1 in the row 3, column 3 spot. And then finally, we produce zeros at the other spots in column 3. Now the reason we want to get the augmented matrix in this form is because if we do, we can simply read off the answers. Remember, each row in the augmented matrix represents an equation. So this top row would be representing an equation that says 1 times x plus 0 times y plus 0 times z equals whatever number is right here. So it would tell us the value of x. Similarly, the second row would say 1 times y is whatever number we have here, and the third row would say 1 times z is whatever number we have here. So the reason for wanting to get our augmented matrix into this form is rather obvious. Let's see if we can do it. We go back to our original augmented matrix, and we want to use the row operations we know about in order to accomplish that objective. In the example that we're starting with, by chance we happen to have a 1 in the top left-hand corner, so we don't need to do anything to accomplish that. It's already there for free. So the next thing we will want to work on is producing zeros in these two spots. And notice we have one of those for free. So to get the first column in the form we're looking for, which is 1, 0, 0, the only work we have to do is to change this 3 into a 0. And we accomplish that by doing row 3 minus 3 times row 1, producing a new row 3. Let's see why that works. Row 3 minus 3 row 1 will give us a new row 3, which is 3 minus 3 times 1. 3 minus 3 is 0. 2 minus 3 times 1 is minus 1. 4 minus 3 times 4. 4 minus 12 is minus 8. Minus 7 minus 3 times 2 is minus 7 minus 6, which is minus 13. Next step. The next step, we'll move over to column 2 and we want to change this 2 into a 1. We do it by simply multiplying row 2 times 1/2. 0, 0, 2 becomes 1 when we multiply times 1/2. 5 becomes 5/2. 4 becomes 2. So we're working on the second column. We've made this into a 1. Our next step will be to make these guys into zeros. We'll turn this 1 into a 0 by doing row 1 minus row 2. Row 1 minus row 2, 1 minus 0 becomes 1. 1 minus 1 becomes 0. 4 minus 5/2 is 8/2 minus 5/2, which is 3/2. 2 minus 2 is 0. So this is the new row 1 when we up here do row 1 minus row 2. This minus 1 we need to turn into a 0, and we do that by getting a new third row as row 3 plus row 2. When we come up here and do row 3 plus row 2, 0 and 0 is 0. Minus 1 and 1 is 0. Minus 8 and 5/2, that's minus 16/2 plus 5/2, which is minus 11/2. And minus 13 plus 2 is minus 11. So we've now finished with the second column. The second column is exactly the way we want it. We move on to the third column. We want to produce a 1 in this spot. We do that by simply multiplying row 3 times minus 2 over 11. That is the reciprocal of this number. So the new row 3 becomes 0, 0. Minus 11/2 times minus 2/11 is 1. And minus 11 times minus 2 over 11 is 2. Almost done. The only remaining work is to turn these two numbers into zeros. This is a system of 3 matrices with 3 unknowns x, y, and z. So when we set up the augmented matrix for this system, we'll need a column for the x coefficients, a column for the y term coefficients, a column for the z term coefficients, and a column for the numbers on the right. The augmented matrix has 3 rows because we have 3 equations, and it has 4 columns. I want to outline the strategy that we're going to use. We start with the augmented matrix, and we'll first do a row operation to produce a 1 in the upper left-hand corner, the row 1, column 1 position. Then we'll do additional row operations to produce zeros at the other places in column 1. We move to column 2 and use a row operation to put a 1 in the row 2, column 2 position. And then we do row operations to put zeros at the other spots in column 2. we move to column 3 and use a row operation to produce a 1 in the row 3, column 3 spot. And then finally, we produce zeros at the other spots in column 3. Now the reason we want to get the augmented matrix in this form is because if we do, we can simply read off the answers. Remember, each row in the augmented matrix represents an equation. So this top row would be representing an equation that says 1 times x plus 0 times y plus 0 times z equals whatever number is right here. So it would tell us the value of x. Similarly, the second row would say 1 times y is whatever number we have here, and the third row would say 1 times z is whatever number we have here. So the reason for wanting to get our augmented matrix into this form is rather obvious. Let's see if we can do it. We go back to our original augmented matrix, and we want to use the row operations we know about in order to accomplish that objective. In the example that we're starting with, by chance we happen to have a 1 in the top left-hand corner, so we don't need to do anything to accomplish that. It's already there for free. So the next thing we will want to work on is producing zeros in these two spots. And notice we have one of those for free. So to get the first column in the form we're looking for, which is 1, 0, 0, the only work we have to do is to change this 3 into a 0. And we accomplish that by doing row 3 minus 3 times row 1, producing a new row 3. Let's see why that works. Row 3 minus 3 row 1 will give us a new row 3, which is 3 minus 3 times 1. 3 minus 3 is 0. 2 minus 3 times 1 is minus 1. 4 minus 3 times 4. 4 minus 12 is minus 8. Minus 7 minus 3 times 2 is minus 7 minus 6, which is minus 13. Next step. The next step, we'll move over to column 2, and we want to change this 2 into a 1. We do it by simply multiplying row 2 times 1/2. 0, 0, 2 becomes 1 when we multiply times 1/2. 5 becomes 5/2. 4 becomes 2. So we're working on the second column. We've made this into a 1. Our next step will be to make these guys into zeros. We'll turn this 1 into a 0 by doing row 1 minus row 2. Row 1 minus row 2, 1 minus 0 becomes 1. 1 minus 1 becomes 0. 4 minus 5/2 is 8/2 minus 5/2, which is 3/2. 2 minus 2 is 0. So this is the new row 1 when we up here do row 1 minus row 2. This minus 1 we need to turn into a 0, and we do that by getting a new third row as row 3 plus row 2. When we come up here and do row 3 plus row 2, 0 and 0 is 0. Minus 1 and 1 is 0. Minus 8 and 5/2, that's minus 16/2 plus 5/2, which is minus 11/2. And minus 13 plus 2 is minus 11. So we've now finished with the second column. The second column is exactly the way we want it. We move on to the third column. We want to produce a 1 in this spot. We do that by simply multiplying row 3 times minus 2 over 11. That is the reciprocal of this number. So the new row 3 becomes 0, 0. Minus 11/2 times minus 2/11 is 1. And minus 11 times minus 2 over 11 is 2. Almost done. The only remaining work is to turn these two numbers into zeros. We'll do that. We'll turn this guy into 0 by doing row 1 minus 3 halves times row 3. 1 minus 3 halves times 0 is 1. 0 minus 3 halves times 0 is 0. 3 halves minus 3 halves times 1, 3 halves minus 3 halves is 0. 0 minus 3 halves times 2 is 0 minus 3, which is minus 3. And the final act of turning the 5 halves into a 0 is accomplished by row 2 minus 5 halves times row 3. 0 minus 5 halves times 0 is 0. 1 minus 5 halves times 0 is 1. 5 halves minus 5 halves times 1 is 5 halves minus 5 halves, which is 0. 2 minus 5 halves times 2 is 2 minus 5, which is minus 3. We're done. We can read off the answer now. The first row says x plus 0, y plus 0, z is minus 3. X is minus 3. The second row says 1 times y is minus 3. Y is minus 3. And the third row says z is 2. You can take these values for x, y, and z, plug them back into that system of equations that we started with, and you'll find that the system is satisfied. We found the solution. If x is minus 3, y is minus 3, and z is 2, then this would be minus 3 plus minus 3 is minus 6, plus 4 times 2 is 8, minus 6 and 8 is 2, and so forth. You can check and see that the other equations are satisfied as well. Now, let's look and see what happens in this kind of situation. Suppose we're working on solving a system of equations by the augmented matrix method, and we've come up against this. Remember that at every stage, each of your rows represents an equation. The fishy thing here is this third row. What we want is if we're proceeding along the method that I've described, we have a 1 and the zeros in the first column where we want them. We have the 1 in the second column and the zeros there. We're at the stage where we would like to produce a 1 in this spot. We can't do that obviously by multiplying the third row times some number, because anything we multiply by is going to leave a 0 here. And if we do a row operation that combines row 3 with one of these other rows, it's going to mess up the work we've already done on the first two columns. So we're sort of stuck because there's not an operation we can perform that will put a 1 in this spot without messing up what we've already done in the first, to get the first two columns looking like this. So what's going on here? If you look more closely at this third row, you'll see that we're dealing with an impossible situation. Think about the equation that's represented by this third row. It would be the equation that says 0x plus 0y times 0z is equal to 4. And no matter what values x, y, and z had, that could not possibly be true, could it? 0x plus 0y plus 0z would have to be 0, no matter what values you put in for x, y, and z. So this row of the matrix represents an equation that can't possibly be satisfied by any values of x, y, and z. So the conclusion you would draw if you came to this kind of situation is that you're working with a system of equations that can't possibly have a solution at all. Now here's a situation that's a little bit different. The bottom row here no longer provides an impossible situation, but it doesn't provide any useful information. The equation represented by this row is just the equation that says 0x plus 0y plus 0z is equal to 0, which would be true for any values of x, y, and z, but it's not useful. It doesn't really tell us anything. The first two rows do correspond to equations. The two equations are shown right here. And by goofing around a little bit, you can find lots of values of x, y, and z that satisfy those two equations. And of course, any values of x, y, and z would satisfy the equation that goes with the third row of the matrix. So, in summary, this situation would be one in which we have an augmented matrix where the system of equations represented by the augmented matrix would have whole bunches of solutions, infinitely many solutions, in fact. What is the strategy for choosing the row operations? You saw me do it in the examples that we've been through. Let's see if we can sort of quantify exactly what I was doing to choose the row operations. Suppose we're doing a problem and we've come to the situation that we're seeing right here. We're partway through the process. We've cleaned up our first column. We've produced the 1 in the first column and the zeros in the first column. We've moved on to the second column and produced the 1 in the second column in the row 2, column 2 position. And we're now ready to pick our row operations to zap this -2, make it a 0, zap the 5, make it a 0. What's the logic that I used in choosing the row operations to do that? It's really not very complicated. The key is I'm using this 1 to do it. And when I want to produce my new row 1, I want to do -2 plus something times this, which will give me a 0. And so what I need there is a +2. The fact that I've got a -2 in this spot tells me that I want to do row 1 plus 2 times row 2, because when I do that, it will zap out this guy, make it into a 0. And for exactly the same reason, when I do row 3, when I combine row 3 plus row 2 to zap this guy, I want the multiplier to be -5. Row 3 minus 5 times row 2, because that way I'll be doing 5 minus 5 times 1, 5 minus 5 to get a 0 in this position. So it really isn't very subtle. The reason this is a +2 is because that's a -2. The reason this is a -5 is because that's a +5. So when you're choosing your row operations, if you'll keep that pattern in mind, there really isn't much to think about. The -2 here determines the +2 in this row operation. The 5 here determines the -5 in this one. And the row 1 and the row 2 are automatic because we're using the 1 from row 2 and we're changing row 1. So when you're trying to zap out this guy, you know you're going to be combining row 1 and row 2. The only question is what this multiplier should be, and it's determined by this being the -2. And similarly for the -5 here. Keep in mind that when you're doing your row operations, you're always basing, if you're doing row operations to produce a 0, you're always doing it by using the 1, which has already been created in that column. Finally, let's look at an example of where you would need to switch two rows. Suppose you're working on a problem and have come to this point. The first column is done. We have the 1 and the zeros in the first column. We're ready to move on to the second column and do something to get a 1 in this spot. What can we do? Well, normally if we had a non-zero number here, like a 5, we would just multiply this row times the reciprocal of that number, 1/5. But if you got a 0, you can't multiply 0 times something to make it into a 1. So that's the situation when you need to think about switching rows. And we can do that here since we have a non-zero number in this spot. If we simply swap row 2 with row 3, that will accomplish the purpose of putting a non-zero number in that spot. So what I would want to do if I was stuck at this point would be to swap row 2 and row 3 to give me a non-zero number in this spot. So this is where I would do the row 2 swap with row 3, do that row operation to move forward. Row 2 switch with row 3 is the row operation needed, and what that means is simply put row 3 in the row 2 spot and row 2 in the row 3 spot.